presentation.
Okay, that's fine.
So you can start now.
Okay. Just see if we can go in slideshow. Okay. So, first of all, thank you for inviting me and giving the opportunity to share our experience in doing lightning analysis with the audience. What I'm going to go through is a little bit of the physics of lightning, but I am being very pleased to see that an hour ago we had a very thoughtful presentation from Dr. Shuri. I don't know if that's the right way to present to mention his name. So I think that the physics of lightning has been already covered quite well, and also, Paul's presentation on the basics of the tool and the lightning is also quite good, because allow me to go a little bit faster in few slides, and then spend a little more time perhaps on other aspects that could be of interest to the audience. So in terms of the agenda, again, it's physics of lightning, the effect of lightning strikes on aircraft, then how it's the lightning being defined in the standards, the limitation of the standards, challenges with modern aircraft and with composite materials. I think Paul has already mentioned that going from metal to composite can affect significantly the way the lightning is propagates. And then some slides on lightning strike current waveform on aircraft, and then some modeling tips in how to use the tool to conduct these studies. So, but first of all, why Rolls-Royce is interested in this topic? Well, Rolls-Royce is one of the main producer of engines, jet engines for aircraft. So if you look at the 747, if you look at the modern Airbus A380, if you look at the Boeing Dreamliners, they're all our engines. And of course, as we all know, aircraft fly in the skies, and on average, they're struck by lightning once or twice every year. I don't know if anyone in the audience has experienced a lightning strike while they were flying. My own experience, I've happened twice for myself, so it does happen, and the statistics are about 1 or 2 strikes per year. So moving forward. So again, the physics of lightning has already been covered in the previous presentation, so I'm not going to spend much time on it. Lightning strike is a sudden electrical discharge between the clouds and the ground. If this is a clouds to ground strike, but there could be other discharge. There could be lightning inside a cloud to balance out the particles, the positive charges which are normally accumulated on the top part of the cloud, and the negative charges which are normally sit on the lower end of the cloud. And somewhere in the cloud, normally there is an isotherm with 0 degrees Celsius, which allow basically the icing particles to melt and basically act as a conveyor belt, as separating and accumulating the charges on the top part and on the bottom part. Again, this is a very, very simplified view. And as I said, the presentation we had before was quite more detailed on the physics of lightning. So normally, the lightning that we see on the ground are negative lightnings, so lightnings where the leader starts from the cloud is a negative lightning discharge, which then gets to ground. But there are also positive lightning, and lightning, as we said before, can happen between clouds and ground or between clouds and clouds. Clearly, in the case of aircraft, we are not only interested in lightning going towards ground, but we are also interested in protecting our engines and our aircraft when the aircraft is in the sky. So we are also interested in clouds to clouds or intra-clouds strikes. Now, positive charges are accumulated on the top of the cloud, and in this case, because of the height, normally the top of the cloud can be several kilometers higher than the bottom of the cloud. So the amount of charge that has to be reached on the top of the cloud before you get enough energy to break the equilibrium and start off this discharge is higher. So normally what you would find is that in terms of the lightning populations, out of 100 lightning, about 90–95% are negative lightning, as the previous speaker said, and about 5% or less are actually positive lightning. But it also needs to say that the positive lightning have much more energy and much more current. So this is a picture which shows the lightning current as defined in the standards, and as Paul mentioned before, it's a waveform which rises to the maximum value, which is defined in the standards to be 200 kiloamps within the first 6 microseconds, and then it does decay to half value at 70 microseconds, and then clearly tails off. Now, if you do a spectrum analysis of that, so if you look at the energy density versus frequency of this pulse, you would see that the higher the energy is at the lower frequency. So as correctly Paul mentioned, at higher frequency you inject less energy. So this graph on this side is quite important to remember when you do an analysis or when you do some modeling. You have to bear in mind this relationship between the time aspect of the lightning and the frequency aspect and the energy density of the lightning. As I said, the main lightning pulse in the standard is called component A, and it's a double exponential with 6.5 microseconds rise to the peak and then 70 microseconds tailing off with a peak value of 200K. Now, the limitation of the standard is that statistics indicate that you can get lightning which are much more energetic. In fact, you can get lightning with peak values of 250 kiloamp or higher. And also you can get lightning which lasts much longer than what the standards define. So you can easily get lightning, this sort of lighting, which can last for 2 milliseconds. The first component, the component A we talk about, which is about 20 times higher than what is defined in the standards. So this highlights the fact that there are some uncertainties on what is the maximum threat in terms of peak and durations, because if you just use the standards, the 0160, you would see that the definition of peak and duration is not necessarily what is the worst case, and therefore when you do an analysis and when you do a design which needs to be robust to lightning, you need to include some pessimisms in your analysis and have some good margins on top of what you have to meet for passing the standards test. So as I said, just to recap, this is a nice pictures because show intra-crowd lightning, so lightning which doesn't close to ground, and it's quite energetic and it's quite cover a very big area in the sky. But as I said, international standards mostly covers negative strikes and not positive ones. Now, why all of this is important? Well, because aircraft normally are on the ground and they take off and then they go up in the sky. And this is a picture which is taken off a video that you can find on YouTube, where a 747 is just taking off, and just a few seconds after taking off has a direct hit by a lightning, which it gets attached to the nose of the engine of the aircraft and attached to the tail of the aircraft. So it's quite a nasty strike. Now, what can this lightning current can do on an aircraft? Well, the most, clearly the simplest one to understand is actual physical damage. When you are hit by lightning, you basically have a sudden rush or inrush of current that you need to quickly distribute away from the point of contact, because the point of contact will start, its temperature of the point of contact will start to rise quite quickly. And if the resistance of the point of contact is too high, so you are not able to distribute the current and take the current away from the point of contact too quickly, then you will get to the melting point of the metal or of the composite structures, which has been hit by the lightning. And as soon as you get to the melting point, then that is where you're going to have significant damage to the structures. Associated with the current and with the temperature during a lightning strike, you also have a shock wave which propagates down the lightning strike channel. So the aircraft structure not only has to dissipate the current and try not to raise the temperature, but also needs to be robust and flexible enough to be able to accommodate the shock wave which is associated with the lightning itself. So you can see here some control surfaces of aircraft which has been blown into pieces due to lightning. Now, those are physical damages, but when aircraft fly in the sky, we need also to consider electrical equipment failure and electrical effects. Now, just to remind that this is not just theory, if we just go back 1 year, about June 2009, we have the Air France 447 flight, which is a modern flight, an A330-200, which is a flight which flew from Rio de Janeiro to Paris and left Rio about 22, so 10 o'clock midnight GMT. Around 4 hours into the flight, the aircraft flew straight into gigantic thunderstorms, major thunderstorms, which were reported in that area. And at 2:12 local time, so quite dark, clearly 2:12 local time, there was a first major electrical fault was detected and sent through the automatic on aircraft. Basically, every modern aircraft has an automatic link to ground, and when there are major events, the equipment and the messages are automatically sent to the ground, informing that there are major malfunctioning on the aircraft. This is without the pilot have to do any action. Basically, modern electronics is such that if there is a major fault, this is immediately sent to base. So we do know that at 2:12, the first of 4 major electrical failures happened, and in a time window of 2 minutes, there were 3 further major electrical faults, and at 2:14, the aircraft went down with loss of all the passengers and crew members. Now, the black box was never recovered because we are in the middle of the oceans. So the hypothesis is that the root cause is lightning, and this has been confirmed or put forward as a root cause by Air France. But has never been confirmed for sure because, you know, apart from the 4 automatic messages which when we went back, we don't have any other records of the aircraft. We've never been able to recover the black box. So what are the challenges on modern aircraft? Well, you know, electronic systems are more and more pervasive. They basically control everything onto a modern aircraft. But in addition to that, modern aircraft use more and more composite materials. The aircraft, the Airbus A380 already has extensive use of composite materials. The Boeing 787 is very much composite all the way through, and the new Airbus wide-body aircraft, the A350, will be fully composite aircraft. Now, what does it mean for us? Well, composite aircraft means that you have a much smaller ground return network. So the electrical network inside the aircraft, which has the role to take away the current from the structures and taking the current from the attachment point to the detachment point, is smaller as compared to a metal skin aircraft. So the entire aircraft has an entire modern aircraft with extensive use of composite material will have a greater overall impedance, both in terms of resistive impedance and in terms of inductance. And if you think about these two, it means that you will have more energy dissipated onto the resistive structures, but also because you have higher inductance, you will have higher voltages which will be generated inside the aircraft. And also you will have oscillations, current oscillations, and because the inductance is higher, the oscillatory current will be higher. And this is what we're going to look in the next few slides. So if you think about the lightning attaching to an aircraft, which is the picture on your left, what you have this current will induce onto the different structures, cables, units, a current which will have roughly the same shape, and it's exactly what Paul has to show you just a few minutes ago, where he was injecting in that simple structure this type of current, and then he was basically seeing that you had a current of this sort distributing across the different parts of the box in that particular case. And also is show that if you use composite material, you see a stretching of the waveform due to the characteristics of the material itself. But when you inject a current like this in a circuit, what you also tend to have is oscillatory effects. And now these oscillatory effects can generate quite high level of peak voltages, which clearly in case of electronic units is a particular threat, because what you have when you have an electronic control system, every I/O will be protected for a particular value of peak voltages. If you exceed that value, you will probably do damage to the electronic units. And also it will have associated energy. So injecting this type of current, you will see oscillatory effects. So when we just the question which was asked at the very end to Paul, why you see a little bit of ripple there? Well, clearly, because of the dimensions of Paul's example, that ripple was almost invisible, and you wouldn't even think to do much analysis on it. But in the case of aircraft and engines, where aircraft have dimensions of 100 meters, and models and engines could be 4 or 5 meters long, 3 meters diameters, and so forth, the oscillatory components could be quite significant. So again, just to go a little bit more in detail then, if you have an aircraft flying and you are next to a cloud, you can have an attachment point, for example, to an engine, and then the lightning strike will then detach maybe at the tail of the aircraft, and this path to ground is called lightning strike channel. and needs to be considered, and its property needs to be considered. But in simple terms, if you look at this model, you have the aircraft could be seen as a capacitor, and the aircraft itself plus the lightning channel could be seen as an inductor. So in a very simplified view, you could see that this is a CL or an LC circuit, and everyone which is familiar with this kind of circuit would immediately think that there could be oscillatory effects in this circuit, which is exactly what waveform 3 is an oscillatory effects induced or by the lightning strike. So what you do is that when you do need to consider oscillatory effect, you need to consider all aircraft. So you need to be able to model the entire aircraft, you need to model the entire engine, and you need to model where the aircraft is positioned with respect to ground. So in this model here, where you need to model basically the aircraft, the engines, because we're interested, or at least Royce is interested in understanding the effects of the lightning on the electronics, which is on our engine. So we will model very accurately the electronics and the path of the engine, but then we need to model the aircraft, and then we need to model how the aircraft is positioned as compared to the ground. So it's a quite complex model, and also the dimensions of the model could be quite daunting, because you can have models which may be 100 meters long or even more, and at the same time you need to model geometries at the engine's level, which could be maybe a couple of centimeters or even less in terms of resolution that you want to achieve. So quite interesting meshing problems. So again, it's quite difficult to carry out a waveform 3 on oscillatory analysis at present. So in the past, something which we tend to use is assume that the waveform 3 threat, so the oscillatory threat, were about twice as high as the waveform 4 threat, which is the nice double exponential current. But this is not precise, so if you want to be much more precise, then you need to conduct a study modeling basically the aircraft in the different flight conditions, ground, takeoff and cruise, different lightning strike attachment and detachment point. So immediately you can see that a lightning strike analysis is not going to be just one run, one simulation, because you probably need to consider several physical configurations with different attachment and detachment points and environmental conditions. So this is something you need to bear in mind, because clearly the time it takes to run a simulations, if you need to run several simulations, then you have to multiply that time for run one simulation by the number of simulations you need to run. So for this analysis, I use two approach. One, to do basic theoretical analysis backed up by SPICE simulation, one using the CST tools to do the analysis, and then I compare the two results. The challenges in carrying out this analysis, first of all, you need to understand the physics of lightning. You need to review all the published data. A good overview was given in the first presentation. And also you need to identify the critical parameters in the lightning, so the lightning channel properties. The lightning channel, for example, have properties which are highly nonlinear and time varying, so the lightning channel's properties change with height and with time. The materials of the aircraft, in Paul's simple example, you immediately see the difference if you use a perfect conductor, aluminium, or if you use composite, so materials, and also physical dimensions. You need to create, in the case I've done, a theoretical analysis, and then the SPICE, and then the 3D analysis. For the theoretical analysis, I've had to create electrical equivalent models. And for the 3D, before using the tool, I had to validate the tool using existing engine data and existing results that we knew were accurate. And once we're happy about how to use the tool and what tips and tricks you need to adopt in order to get a good correlation between the results from the simulation and real data. Then you can run the models for the exam question that you are asking yourself. So in the case of the lightning strike with the oscillatory waveform, again, this is just a very simplified view of a lamp circuit of the system. Not going to spend much time trying to describe it, but it's a quite complicated model. This is just a simplified view of it. So the model becomes quite complicated. And what you tend to see is that once you inject this type of lightning, you find that the worst condition for flight is when the aircraft is near the ground, which basically means you have the maximum coupling between the aircraft and ground. So the capacitor effect, the capacitance of this circuit is maximum when the aircraft is close to ground. Clearly, this means that in case you have a big aircraft, because of the size, that value of capacitor will be bigger, and also the positions of the lightning strike connection is quite important. In our case, where I was interested in looking at the effects onto the electronics onto the engine, the worst case it was when the lightning was attaching to the body of the aircraft and detaching from the engine. And this you can see one of the simulation outputs. And what you find, or what I did find with a particular engine and with a particular aircraft, was that the relationship between the waveform 3 oscillatory components and the DC values of waveform 4 is about 1.35 as compared to the value of 2, which otherwise you would need to consider in case of worst case. So clearly this analysis allows you to be much more accurate. And as I said before, remember that because the energy density is higher or lower frequency, anything you do which makes the resonance of the circuit going low in frequency means that you're intercepting more energy, and therefore it is going to be a worse condition. So now you go into 3D modeling. We import a full engine model. This is just a simplified view. Again, clearly, for confidentiality, we cannot show, full models. But this is a simplified view where you can see an aircraft jet engines. You can see a box up here, which is the electronic engine control unit, which basically controls the aircraft. You can see a number of wires. Clearly, this is a very, very simplified view. But for example, in yellow, you can see how the current would propagate when the lightning strike attached the drain mast, which is a metal pipe which sticks on the bottom of the engine, or if the lightning strike is attached to the plug. And if you run the simulation, you can have very accurate definitions of the path of the current, and therefore how the current will couple into the different cables, because as Paul mentioned, what we are interested in when we have electronic units is the current which couples onto the different wires. So we need to understand how the current propagates into the metal structure of the aircraft onto the engine, and how then this current couples onto the wires, in order for then understand how this impacts the electronics inside our units. So this is an electrical field around the engine, and it's interesting because in this particular simulation we were looking at unshielded harnesses. There could be few places where you need to have a little bit of unshielded harness just to get to where you want to be, but clearly unshielded harnesses are a concern, so we need to do quite detailed analysis to understand what happens to the induced voltages and therefore induced current and therefore voltages in these cables. And the tool is very, very powerful in doing this kind of analysis. Modeling tips. Clearly, the first modeling tips that I have is try to understand what are you trying to model. What is the physical dimensions that you need to model, and with what resolution you need that model to be. Because clearly, if you have a very, very simple model in terms of dimensions, something which is, a meter or half a meters, that's fine, and you can use quite a good mesh, and the time to run the simulation is not a concern. But when you start modeling, for example, a car, so dimensions of 5 meters by 3 by 2, or if you're trying to model an entire aircraft or an engine of an aircraft, dimensions we're talking about could be 4 meters by 3 by 3 in diameter. So you're talking about big dimensions. And then if you want to model the environment, you may model something which is 100 meters. So clearly you need really to understand the dimensions of your problem and understand how these affect the meshing. Because the first thing you need to do is to try to simplify as much as possible your model. In our case, for example, when we were trying to model the effect of the aircraft in the engines, because Royce is interested of what happened on the electronics onto the engines, we didn't need to model the aircraft to a lot of details. So you can use a very simplified model of the aircraft. This is because we were not interested in knowing what happened onto the aircraft electronics. We were interested on modeling the engine electronics, and therefore we were using very accurate models of the engines. But the further away we went from our interest, the simplified the models will be. It's key that you optimize the mesh. So Paul mentioned one thing about frequency. Clearly, if lightning strike, as we just said, is a relatively lower frequency content, but depend on the dimensions you have. You may exercise frequency, which can be 10 megahertz, 20 megahertz, 30 megahertz. So, but you need to be careful, because if you put a higher frequency, if you're trying to run a simulation with a high frequency boundary, the time it will take to run the simulation is going to be longer, and the mesh elements is going to use smaller mesh size. So you need to understand, have an idea of the frequency that are going to play your model, and therefore try to use a bandwidth which is correct for the problem, but don't overshoot, because it's easy to say, well, it's a low frequency problem, but I want to capture everything, so I'm going to set a top frequency 100 megahertz, for example. And it's fine if the model is very small, but if it's moderately big, that will kill you. The mesh size will become too small. So you really need to understand and optimize the mesh, because mesh size dictates how long a simulation will run, or is one of the elements which will dictate how long the simulation will run. And you don't want to run simulation which takes more than 48, 50 hours. Basically, our target is, within Royce, we try to, the longest simulation we want to run is something which, we set up on the Friday and we want to have results on Monday. If it takes 2 weeks to run a simulation, that really is start to become unacceptable, because remember, you want to run several of those simulations. So you need to have simulation we run over the weekend, worst case, but ideally which are able to run in a couple of hours, for example. Use cable models when you have small cable bundles. The CST tool has a very powerful capability of modeling cables in a very simplified way, and if you can use that, use it, because simplify your model and accelerate the speed of the simulation. So if you have small cross section of cable bundles, then I would encourage you to use cable models, because that will speed up your simulations. Of course, if you have big cable bundles, so if you have a cable bundle, which is 2 inches, 5 centimeters cross sections, it is hard to use a cable model for that, because if you use a cable model for that, then the mesh size needs to be quite big, and if you have a very big mesh size, you wouldn't be able to resolve the structure of your engine. So, if your engine dimensions, the minimum dimension you want to resolve is a couple of centimeters, you cannot have a mesh size which is 10 centimeters, because you cannot resolve 1 centimeter's physical dimension with a 10 centimeter mesh size. Then you have to run the simulations, but run the simulation just for the time you need. The example that Paul showed, for example, before, you had the simulation which was running for 100 microseconds. Now, in Royce, we would tend not to do that, because what you would try to do is say, what is the part of the simulation where you really get the maximum data out? And normally, for a lightning strike where you have a peak at about 6 microseconds, if you run for 8, 10 microseconds, you normally can capture most of the effects. I accept that sometimes you see that some of the current haven't yet reached the maximum. If that happens, then you need to stretch the time, but try not to run for the full windows. If the peak current is at 6 microseconds, then it's a good advice, at least at the beginning, just run for 8, 10 microseconds. Don't run for longer than that. It's just to keep your simulation, manageable. Try to do a lot of quick trials. The last thing you want is to create a gigantic model and then mesh it, and then you find that the mesh doesn't mesh because create a monster that you cannot simply simulate. So, try to create the model and try to create quick trials. Mesh it, doesn't work, remesh it, refine it. Try to use the cable models. Try how much you can stretch and use the cable model, and when you need to stop and start using pipes. Try to do lots of quick trials before you run the full simulations, because and refine your model. I find quite useful to use variables in the CST tools. Again, for those of you who doesn't know what I'm talking about, is basically you can parameterize some of the dimensions so that whenever you need to do some changes, rather than to go and change some of the physical dimension, you can just change some variables at the top menu and the model automatically adapt. I found that quite powerful. Although unfortunately you cannot use variables for circuit components. So one of the features you can do in CST is to define small circuits. But unfortunately, on the version 10, the version which we have, you cannot, put variables on those electrical components. But on top of it, be patient. With lightning and with modeling, things will not usually work first time or second time or third time. So be patient, understand what the tool can do and cannot do, understand what is the strength of the tool and what are the limitations of the tool. If you run into problem, you can't really get out of it, then call the CST guys, which are normally quite helpful. But they are challenging. Lightning is a challenging problem. It requires a lot of understanding of the physics, on the modeling. So you need to be patient, but at the end, you can have some good results. And with that, I finished. Any questions?
Thank you very much, Claudio, for this very interesting presentation. Maybe one question, if there is one. Yeah.
Clearly, you need to replay back the question to me over the phone.
Yeah, I will do.
Okay. If my understanding is correct, you are including in your model the aircraft to see the effect of waveform 3. Satisfied given the aircraft. Is this waveform 3 here? What about waveform 4 and 5?
So the question was, have you modeled the complete aircraft with waveform 3? To see the effect of waveform 3? And what about, yep?
The model we have done, so when we have done the model, we have done the model having a complete and exact model of the engine and a very simplified model of the aircraft. But the dimensions has to be correct, the materials needs to be correct. Now, the fact that we haven't modeled the aircraft in a lot of detail is simply because as Rolls-Royce, we are not interested in knowing what happens to the electronics inside the aircraft. We're interested to know what is happen to the lightning strike effect on the engine. So we have modeled the engine, all the electronics on the engine, all the cables on the engine, everything else. Of course, we are not responsible for the aircraft electronics, so we model the aircraft much in a very, very simplified view, but you still need to make sure that you have the right dimensions and the right materials, because otherwise, the simulation is wrong. When you inject the component A, what you get, and you model the whole environment, because remember, then you have to model the engine, the aircraft, but then you have to model how the aircraft is positioned as compared to the environment, to ground. Is it close to ground, or is it flying to the sky? And where is position as compared to the lightning strike attachment point? So the model can be a quite big model as soon as you start modeling, for example, an aircraft which is 10 meters from the ground or 50 meters from the ground, taking off an engine, an aircraft which could be, as I said, 100 meters in dimensions. So yes, we have modeled the entire aircraft. Yes, we have modeled the aircraft into the environment, but no, we haven't modeled cables inside the aircraft and electronic units inside the aircraft. But what you see when you run the full simulation, you not only get the waveform 4, because when you inject the lightning, the simulation doesn't know which waveform we want. You basically run a full simulation, and you can extract the waveform 4, waveform 3, waveform 2. You can basically see all the components which makes the lightning strike onto the aircraft to be shown by the simulation. So it's quite powerful.
Thank you, Claudio. Thank you. I think we have to proceed because we are a bit late now.